I'm Cindy Kelly, Atomic Heritage Foundation, and I have with me David Holcomb. First question for David is to say his name and spell it.
My name's David Holcomb, David Holcomb.
Terrific. Now I want to know something about yourself, like where you're from, when you were born, and then what sparked your interest in science.
I'm an Army brat, so I kind of lived around the world. I was born in Fort Dix Army Medical Hospital, so I moved around with my family as my dad changed posts around the world, and I was always interested in science. And somewhat, my parents, sparked that. My dad, also has a PhD. And when I was 0 to 3, we lived up at the University of Wisconsin, where when he was getting his PhD. So I'm kind of brought up. My mom also has a science bent as well, so it's kind of what the family does there. My brother always describes himself as the least educated person. He only has the master's from Caltech, so so it just is a part of the family tradition. And I kind of got interested in energy just from reading as a child. Growing up, I looked at some of the things like Isaac Asimov's. He did some estimations of what what free energy would do for the world, and I sort of got interested in what you really could do if you could lower the prices of energy, and saying that, well, I got to work on something. Why don't I work on something that I believe in, that I think is important, and providing large quantities of energy to help humanity sounds like a really good thing to work on. And when I was at the point of what do I decide, I started this probably 7th grade, I believe, is when I decided I wanted to start working on energy. So this is what I wanted to do.
That's fabulous. Well, then, when did you you got your PhD, and then what happened?
Well, it was the early 1990s, and as you might know, nuclear was really in a dark spot at that point. This is just as the nuclear energy research was being killed off in the Department of Energy, and so at 97, Clinton had taken it down to 0. And so I was desperate, trying to find a job, and went into a postdoc in radiation oncology. But fortunately, the NRC was continuing to fund research, and turns out ORNL had a spot. They needed someone who could do nuclear instrumentation and controls for nuclear power to help them, and so they posted an opening. I applied. So I came here right after I didn't actually complete my postdoc. I just, so basically out of graduate school, straight to ORNL, and have been here since then. They reorganized multiple times, but I have continued to work on nuclear power, instrumentation and controls, general advanced reactors, molten salt reactors, really become my focus since about 2005. I have to thank the number of the people who I've worked with Sid Ball, who was one of the original operators for the MSRE, and you can take much of his, you can get his name on a number of the reports on the instrumentation controls for the molten salt reactor. And he joined in the lab in 57, and he's still a casual employee, I believe it's called. So he comes in every once in a while. And then Charles Forsberg, he was one of our corporate fellows, and he's invented the fluoride salt cooled high temperature reactor along with Per Peterson and Paul Picard from Berkeley and from Sandia respectively. And so he then was our lead for much of the technology, and he encouraged as he left to go to MIT, and he retired to be an MIT professor. So not exactly a low-pressure retirement, but when he left, I then took up a number of his roles. And then because we are here in Oak Ridge, there are so many people who have such history in there. Whether Dave Williams is one of our salt chemists who's just extensive knowledge on molten salt reactors, and he has now moved into other areas, and and we can trace back our history of the number of people. Jim Rushton was my division director who managed the cleanup activities at MSRE and encouraged me to become more knowledgeable to be able to support the DOE ongoing activities. So it's just a rich opportunity. I mean, my group leader for almost 15 years was Gary Mays, and when he was first hired here, his job was to run the tritium collection loop. Is one of the challenges for molten salt reactors is they generate tritium, and particularly thermal spectrum reactors, which we were running on. And that tritium production, we have to prevent that from getting out into the biosphere. And his first job in, I believe it was 74 when he was hired, was to be the engineer running the tritium collection loop. So you just, everyone you tie to such a rich collection of people here. So day one, being hired here, I had people who were at, one of my close colleagues, Dick Fox, was at the Chicago Pile. His name's on the Chianti bottle. You just don't get that very many other places.
That's very exciting. Talking about history, why don't you tell us, what is the history of the molten salt reactors?
Well, there were a couple of people, actually. It kind of helps. You have two Nobel laureates, Eugene Wigner and Harold Urey, who really thought initially that you always should have had a liquid fuel. These are basically a chemical reactor, and we add the nuclear to it. And other people thought that these were really mechanical systems. But we always had a couple of people in the Manhattan Project from day one who thought really should be a liquid system, because we really want to be able to take the fission products out and manipulate what the fuel is. And so we've just been building from the beginning of the nuclear era on how do we go ahead and make a reactor. And so the history kind of is, well, initially, we in the Manhattan Project, of course, they were trying to make weapons, but that really, they had their production here, and that was the graphite pile and such that was going on. But following this, the U.S. then was trying to initially come up with a way of keeping its nuclear deterrence alive. And so they didn't have ICBMs back then. And so they were trying to keep a way to keep the aircraft up flying. And so we had the nuclear bomber program that existed until 59, when we had developed ICBMs. And so we were trying to create reactors which could fly and which would stay aloft and be able to deliver a nuclear weapons payload. That paid for a lot of the original technical development. Frankly, if you read all of Weinberg's notes from there, he was the lab director at the time, who was really the person who pushed molten salt reactors. We knew this was probably not going to be the best way of doing that, because of the requirements for shielding just are not really well compatible with flying. But on the other hand, the Air Force had an awful lot of money and was very interested in pursuing the technology, and so we were pushing it forward. And in 1957, there was the Fluid-Fueled Reactors Task Force, which really tried to look at, okay, if we're going to look beyond the light water reactors, which we're always going forward, what are sort of the options, and what would be the best thing? And the molten salt reactors were selected as the most technologically useful option on there in 57. And the U.S. program largely grew out of that, the decisions. And so in 59, I think it continued in small phases until 61 with the aircraft reactor program. But it really had transitioned by the early 60s, into a civilian program. And we got authorization to build the MSRE, I believe it was 61. And between 61 and 63, then they're doing the design, and then at 64, the construction's going, and then by June of 65, they have first criticality. Now, while that's very impressive in any case, just from the rate on there, to understand how much the aircraft reactor program provided as a tail, has provided for help on this. We ran the aircraft reactor experiment, I believe it was 54. We ran a number of hot criticals and cold criticals as part of the aircraft reactor experiment. So there was a very large program. I believe we ran 25 pumped loops. We run a number of loops within test reactors. The materials test reactor at Idaho, we ran a number of different loops with different materials, different salts. So it was an extensive program. I can find natural circulation loops numbered, and the numberings go over 1,000. Now, unfortunately, I can't find all the paperwork, so I don't know whether this is a continuous numbering on there, but I would not be surprised if we did not have over 1,000 natural circulation loops run in the 50s and 60s. Excuse me. And so there's a huge history on this, and we develop many of the things like the advanced nickel-based alloys have much of their origin in the salts because the chemical compatibility of the of nickel-based alloys with the halide salts are is a key technology to allow you to contain the salts and for them not to corrode extensively. Largely by the early 70s with the MSRE, we mostly mastered the technologies. I mean, the MSRE was an incredibly successful operating test reactor. And so we generally understand the physics and sort of the chemistry of running a test reactor. And so today, today's challenges are how do we go ahead and take this from this small test reactor that ran it from a limited period and get something which is economically competitive and can rerun for a long time at large scale. That wasn't done, and that's what we need to do. If somebody, frankly, we're a capitalist society, and if somebody can't run this and make money, we're not going to do it.
And that's what happened in...
You say, and we had a couple of times things stopped. I mean, we really thought we were running out of uranium in the 60s. We really did not appreciate how much uranium there is in the world. And so we were really trying to breed more uranium and to create more fissile material. And so that was the focus of the molten salt reactor program, was trying to use thorium and breed it into uranium-233. And so we were focused on that technologies. At that point, essentially the weapon states were us and Russia. And then China came in, and India, the UK, and but we weren't nearly as concerned about rogue actors on this. So we weren't really. It's just a different world today, and it was President Ford who gave the big speech on plutonium, the plutonium economy, and his decision not to pursue the plutonium economy. And so we just weren't in the president's 1977 budget because molten salt reactors were perceived to be too high of a proliferation risk. And indeed, the reactors that what we were trying to pursue at the time, it was called the Molten Salt Breeder Reactor Program. We were very much trying to breed more fissile material on site. That is very much not the case today. We recognize the environment that we live in and the risks that the world has. And, well, frankly, we also realize the world's got an enormous amount more uranium than we thought, and we can't come up with any scenario, particularly now that we can get uranium at a reasonable price from seawater, that we're ever going to run out of uranium. So we look at, in these reactors, it's not necessary to have a breeding system, so we don't design and we don't include that in the reactor design. And some of these reactor companies are trying to even get rid of the enrichment part and say we can feed natural uranium in and get rid of all of the centrifuges, which are currently one of our most vulnerable parts for proliferation, is the enrichment part. And if you can get a reactor which allows you to breed but not separate the fissile materials, you can get rid of the most vulnerable part of the proliferation. And so we're trying to become a positive force on proliferation instead of a negative one, which was historically there are risks if you create separated streams of fissile materials. We think that largely they are some of this is perception because of the extreme radiation environment and the particulars of the details of the reactors, that would be very difficult to use for weapons production, but it's not impossible, and that's the type of decisions that political people make, is whether we pursue actions or not. And following the closure of the program in 1977, there were a couple of reactors that were developed. Largely, I have to give credit to a few of the folks like Dick Engel, who was one of the inventors of what's called a denatured molten salt reactor. And essentially, what they've done is taken the breeding part out of it and just said, well, we just allow the fission products to build up. And we never separate them out. We never separate out protactinium. We're not trying to be a reactor which creates separated fissile material. Can we still run as a useful reactor? Certainly seems so. And several of the current companies are trying to make businesses out of that. If you look at whether it's Terrestrial Energy or Thorcon, there are a number of the companies that are private companies that are trying to make a business out of what's largely the denatured molten salt reactors. And I'm actually very thankful they credit Oak Ridge very publicly about this as ideas. And this is well, yeah, we probably can turn this in, and TerraPower is also building on some of the history with fast spectrum molten salt reactors and their own version of not having fissile material separations.
So, for the elementary school watchers, can you describe the difference between your molten salt reactor and, let's say, the light water reactor?
Well, in a light water reactor, the fuel's in rods. It's a solid object, and they're rods, and it's cooled by water flowing through it. In our reactor, well, the fuel's already a liquid. And the nice thing with our liquid is that the liquid doesn't boil until very, very high temperatures. In our case, typically around 1400 C. It's very hot, and there essentially the reactor vessel softens and melts about the same time that the salt would boil. And not being boiling means that our fluid is at very low pressure, meaning atmospheric pressure or less. And the advantage of atmospheric pressure is that there's no real force to cause radionuclides to leave. So unlike a light water reactor, which has a reactor vessel, it's about 6 inches thick, it has a number of safety systems to really make sure that the water stays over the reactor core and that you always keep it covered. And these safety systems end up making the reactor expensive, and it also has very thick-walled containments. And so the modern light water reactors have ended up being a very safe system, but they are ending up being more and more expensive to generate power. And so what we're trying to realize is that if you get something which is a liquid and in low pressure, and we can't come up with a way of having a large accident, well, I don't need to have safety systems to prevent accidents that we haven't been able to come up with yet. And as long as we can't come up with any serious accidents, we think it should be a much cheaper system. And so our real big difference is our fuel's a liquid, and the fuel moves along with the coolant. And in a light water reactor, the fuel and the coolant are separate, and only the coolant moves.
So, in a reactor, so you have a containment vessel that contains this, but interior to that, inside, is just heterogeneous liquid.
In our system, there are two general parts in a molten salt reactor. Two classes. One of them's a fast spectrum reactor, and that means that it stays critical on neutrons, which have high energies, and that allows you to use U-238. Essentially, allows you to get a positive breeding gain from natural uranium, and in that, essentially, it's just the liquid inside. And then what you have is the liquid. There's fissions that happen in there. It heats the liquid up. The liquid is pumped around. It goes through a heat exchanger, and in the heat exchanger, your primary coolant salt then absorbs the heat, and then the coolant just continues, and then the fuel salt just recirculates back into the reactor core. In a thermal spectrum reactor, you also have to have a moderator on there, and in most cases that's graphite on there, and the graphite goes ahead and brings down the neutron energy to where fissile elements, you don't have to use a fast fission, and you just have much higher cross sections, which means you need a lot less fuel on there. And so it's uranium-235. it looks an awful lot like compositions of the uranium content in a light water reactor, and you bring that in and you cause the fissions with a thermal spectrum. But otherwise, the fuel itself is a liquid. But most of the core in a thermal spectrum reactor, if you look at it, is essentially graphite blocks with holes in them, so the liquid will flow through it. Well, essentially, right now, light water reactors are mostly a mature technology. We're in the process of making them better, and I will say the Gen 3 reactors are, they're Gen 3 Plus, have some substantial improvements over the earlier ones. On the other hand, the early reactors work pretty well as well. Our problem comes out to is they cost too much is right now. I mean, people can make very strong claims that the U.S. market is broken on the price, and that's why we are closing down so many reactors in the non-regulated markets. But fundamentally, we're trying to get to the point as an industry we'd like to be able to be the cost-competitive option. And so that's always the drive: is how do you lower the price? And if you are continuing to be burdened by more safety regulation and more, procedural requirements, it is very difficult to win, because those aren't engineering things where I can make a better thing. Because every time I do something for engineering, it costs more money. And so what we're trying to do is you change the game. Something where we can't come up with having the big accidents. If we don't have the big accidents, I don't need to put in a safety system to prevent them. And so that's really is the focus, is we need to be able to make the next generation of nuclear entrepreneurs successful to say, hey, we're going to generate large quantities of electricity. And we also need to do it in a way that is highly proliferation resistant, so that the U.S. would be supportive of deploying this around the world. Because if we look at what's going to happen when the rest of the world reaches our level of development and the amount of energy in there, if we do this with fossil fuels, we are going to be sending so much unpleasantness up into the atmosphere, whether it's CO2 or particulates or SOx or NOx. We really don't want to run that experiment to find out the details of what's going to happen with that. And so we're saying, well, nuclear is the clean air energy that doesn't take massive quantities of land and massive quantities of concrete, which are, if you look at the solar and the wind, well, there's some real challenges with dense societies and dense industrial areas, but you also just look at the physical infrastructure, because you've got a diffuse energy source and how much concrete it takes to build this system. And we really would like to nuclear has the advantage that it's a very compact energy source. You have a very small area that produces an enormous quantity of electricity. And we want to take advantage of that and be able to help all these people and help them bring up their standards of living. I mean, there's higher correlations with available energy than about anything else with the well-being of society there. If you look at, even healthcare or in food availability, apart from just the basic nourishments, energy availability tracks so well with a helping of humanity. This is such an important thing for us to do.
It's true. Well said. What is this you're involved in looking even further with the Generation 4 international?
Well, this is one of was part of President Bush's initiatives. We're trying to see is how can we cooperate around the world. In the Generation 4, we were trying to look at the second Bush, not the first, but he was trying to look at how can the world cooperate on nuclear power, and what are the mechanisms. And so we looked at what are the classes of advanced reactors that might be done in the future, and there were 6 reactor classes identified, one of which is the molten salt reactor. And so there are a number of countries that have had a molten salt reactor programs, but because it takes a fair amount of engineering effort to go ahead and take a reactor class from essentially PowerPoint today into a real system, everyone was running these sort of subcritical effort levels, and we're never going to get to an actual deployment from a government push perspective. And we're trying to say, well, can we combine some efforts and see whether we can't get further? And there's also, to some extent, there are a number of things that, as far as the safety, the proliferation resistance, that the advanced countries all agree on. Can we take a common approach to this? And so we have a number of the efforts. I mean, the Russians are a major player in molten salt reactors. The Chinese have got a fairly large program, and we don't ordinarily cooperate extensively except in basic sciences. But some of these things, like again, reactor safety, we'd very much like to make sure that we have common approaches to these types of things, and so we want to cooperate where we can. And so the Generation 4 International Forum provides that vehicle, and because we've had the U.S. Senate has approved the framework agreement for the Generation 4 International Forum, it provides us a vehicle so that we can cooperate on specific technology developments internationally. Under, of course, DOE is the implementing agent for this, and so it's under the guidance of the Department of Energy on what we would cooperate with other countries. But this is, again, it's an indication that much of the world can see that this is an important subject, but they can also see that there are technological challenges in this. And in some ways, everyone refers back to Oak Ridge because this was the only place that's ever actually operated a molten salt reactor. And so, again, the other reactor classes are also going forward in the Generation 4 International Forum, but our real thing that we think molten salt reactors the effort is to try to get them to be economically competitive. And we hope that we have that advantage as a low pressure system that provides high temperature. So the technical term is high exergy energy, because a high availability ability to do work with the energy, which is a distinctive characteristic of the reactor class.
So how does a molten salt reactor address the nuclear waste generation issue?
Well, it largely is, if you look at this, the fuel doesn't actually build up any radiation damage. And so if you look at things as what's going on in the fuel, essentially you can keep using the fuel. And so even in the next reactor, where did you get the fuel from? Well, in the breeder reactors, the concept is that you produce the fuel in the prior generation reactor, and so that largely the waste is the fuel to allow you to create an expanding program. And you don't actually end up with any of the fuel waste until somebody decides that molten salt reactors are no longer the energy source that we're going to be using for the world. And we're hoping that's a very long time from now. And so that there is not a substantial high-level waste program, because essentially the fuel is used in the next reactor and the next reactor and the next reactor. So we largely, it somewhat sidesteps it, because it does mean at some point if fusion is ever working, or if we ever have some other very large transition, then all of a sudden all of the fuel salt in all of the reactors then becomes waste. There is some advantage that we happen to know almost all of our fuel processing technologies are based upon the molten salts, and so it's one of the easier ones. If someone had to create a waste processing system, our reactor would be one of the ones that'd be easiest to do that with. But again, mostly the vision is just avoid needing to. If you feed, if you can, because we would like to think we're going to have, our challenge is going to be creating the initial fuel, and saying that, well, the next reactor is largely going to get its fuel from the prior one once it's irradiated the reactor vessel and the materials within it so much that they need to be replaced. Well, we just put a new one in, and it's a liquid. You pump it from one to the other and move it on to the next generation.
You might have a succession of...
Yep, and hopefully a growing one. Say the breeder reactors are really trying to feed, how many years does it take to generate enough new fuel to feed a daughter, and then the two of them working together to feed another daughter, and then the three reactors to feed the next and the next, and keep producing more and more. On the ones that are burners, which are the thermal spectrums on there, they would still need to be fed with somewhat low enriched uranium on there, and so they would continue to rely upon this. But you could still, say, use much of the fuel that was in the prior generation and feed it into the next one, because it doesn't stop being good fuel just because I've now irradiated the graphite so much that it's no longer mechanically useful. It still becomes good. It was still good fuel at the end of the other reactor. Well, it's still good fuel in the new one. Some of the challenges that we're still looking for is, one of the things is that we are now in a light water reactor environment in this country, because those are the only reactors we've deployed commercially. So one of our challenges right now is helping the NRC develop a licensing framework which is reflective of the safety characteristics of the reactor class. Because light water reactors have the potential, while it's remote, of having these large land denial accidents, all of the regulatory structure is built based upon, well, what do you have to do to show that you've adequately prevented that? Well, if you go ahead and you pile all those requirements on something which doesn't need that because it doesn't have the accident possibilities, you make your reactor so expensive that it's don't build it. And so that's one of our big challenges today. Another one of our big challenges is that we've lost the supplier base in this country. I can't buy, if I need 20 tons of salt reactor fuel, well, there's nobody who sells that in the quality that I need there. There's nobody who sells the reactor vessel in the form, all these things. And we're having to essentially bootstrap the industry up. And so there's a lot of challenges today about which are really being borne by these first-of-a-kind developers trying to say, well, I have to have a reactor vessel, I have to have a pump, I have to have this heat exchanger. I only need one of them right now, and people charge them for one-of-a-kind specialty items, and it makes these things very expensive. And so they have an uncertain licensing path, because we don't know how much time or money it's going to take for the NRC to change into essentially a performance-based, risk-informed licensing path instead of its current prescriptive, you must do it this way because that's an acceptable way for a light water reactor. It would be acceptable for us. It would just be so expensive that would make the technology infeasible. And so as our big challenges are both get the licensing aligned with the risks of the real technology, and then get a supplier base developed so that people can see, well, if I invest money in this, it may be a very expensive thing, but if we look at, there's a lot of capital in this society. Look at how much the oil industry spends on something like a refinery or a new gas field. We're at the same type of time frames for payoffs and the same amounts of money. The problem is the lack of certainty that they're going to get the payoff. They're very certain on if they go to a gas field or they do a new refinery. Well, in 10 years, this is going to turn around and it's going to start pumping money back out. And unfortunately, with it being a regulatory hurdle, we're in the spot where we don't know how long it's going to take. We don't know how much money it's going to cost. And by the way, we can't buy the pieces, so I can't tell you how much it's going to cost to construct this either. And so right now we're caught in an uncertainty hurdle, and that's where the DOE efforts, trying to help, we're saying is how can we support the NRC to provide the technical evidence so they can adjust their rules based upon they are dedicated to protecting the environment and the people, and so we have to have the evidence for them to say, well, this is what the rules really should be. Well, you have to have high quality evidence all the way through every accident scenario, every piece, and so that's part of what the DOE campaign is doing, is developing the evidence. We're also trying to provide the evidence of, well, how can you apply modern manufacturing techniques? How can you apply modern designs? I mean, one of the things that we have is we know that some of the components in the system are not going to last the life of the plant. The reactor vessels probably are going to need to be replaced several times. This is an extremely radioactive environment, and we're just not going to have workers in there. And so that means we're going to need to do this all automated. Well, in the 60 years ago when we were building these things, we didn't have automation. We didn't have the advanced robotics. Well, we have to use very specialized advanced robotics because of the extreme radiation environment. But things like just up the hill, the spallation neutron source, well, its target exchange capabilities uses an extreme radiation environment advanced robotics system. That's something that was done in 2006. That's much more recent, but we can apply those technologies and try to help the industry understand, well, what does it really take to do this? And so to some extent, there is private industry leadership, but right now it's all at the very risky end of venture capital, and it's also not as commonly known. I mean, there just aren't that many people in the advanced nuclear power business, so it's harder to get, the set of venture capitalists to say, well, yeah, this is where I need to go, because they know the IT industry and they know in 18 months this is our time frame. Well, we're in the 15 years. This is our time frame where you're going to start making money. You might be able to put a test reactor online at a much shorter date, but you say when I start to have to make multiples of these to make money, your payback windows are longer. And so I have to say we still are in a high risk area, and we're hoping through the DOE program to buy down some of that risk to allow the private industry to be able to be successful.
So you know from conversations with the private sector, there are companies who want to get in this game, or
there always are, and some of that is the nature of the U.S. that we have all these bright startups. The challenge on some of this is getting that combination of enough experience and enough engineering depth to say this is a large, complicated endeavor, along with enough capital to keep going for a while. There are multiple companies that are, some of them are at various stages, and some of them are backed by, very wealthy individuals, and it is an interesting time. Don't know whether anyone is going to be successful, but I don't see any fundamental technology reasons why they can't be.
And since it's all about pricing, we don't know, what's going to happen to natural gas. It's gone up and down. It's low now, but same with oil.
But that also sets a target for us. They still have to pay for fuel. We still are a high temperature energy source. Most of the economic models that you see from these companies say we should still be able to be competitive even with low price natural gas. And so I'm not going to just give up on beating natural gas on here. On the other hand, you're correct. It's a very low price. It's a very long thing. On the other hand, if you look at most of the models, they tell you in 35 or 40 years, even with the fracking revolution, we will still have a lot of natural gas available, but the price is going to go up. And that's part of the reason I think see some interest, because the oil majors want to stay in business, and they know in 35 or 40 years they're going to still have to be going after providing energy, and they're going to say, well, we need to start investing now if we're going to have, what are we going to do next? If we're going to run out of hydrocarbon resources, or at least the hydrocarbon resources are going to become markedly more expensive, that's not an indication of don't invest, because long term our companies are in the energy business. And so I'm not, I don't think that low price natural gas is the death knell of this, both from the, if you just, the basic economics on if our fuel is very low cost. The price of the uranium in the nuclear power even today is like 0.1 cents per kilowatt hour. It's just it's a very small amount of the price. If we can make most of the rest of this, because we're a low pressure system where you've paid some capital costs up front, but we've radically reduced them because we have very much lower amounts of materials, because we're low pressure, we're high temperature. We also try to very much improve our security parts, that there isn't anything for anybody to go blow up. So I don't need to have the security force that other places have because, the technical term is we have no vital areas that are accessible, which means that there isn't something. And so we're hoping to rely upon the local police to provide our defense, just like other industrial plants, instead of having to have your own security force, which is what we have to have in today's plants. So it's another major cost. Again and again, we come back to is we have to lower the price of power, and therefore going to be competitive in the market.
Well, it sounds promising.
Say we're in an interesting time. I hope that we are successful. As all the nuclear engineers probably since the last light water reactor eras I'm worried that your career is going to be a failure in that right now no one's built an advanced reactor. There are no molten salt reactors on the grid generating power. And I really want that to change. Otherwise, you have this, possibilities of negative results of all these years of effort of so many people. Sure, why so many people are interested in this is we very much want to see, success, and not just success in the government. Because we built and ran the MSRE as a government institution. It worked exceptionally well. It's the best run test reactor I've ever heard of on its performance characteristics, and yet it didn't go out on the market. That says our government, purely government solution is not the answer. Our answer now is we need to get the private industry into this, building these, making a profit, and selling power to the people.
Well, I certainly hope that works.
As do I.
Right. From all I read, we just can't make it in terms of meeting the world's energy needs, and probably not the nation's energy needs, without having some form of nuclear energy in the mix.
Again, all the projections are there. These are societal choices. We can become a much less industrial society, and that is an option. I don't think most people want that. I certainly would like to continue to have the advantages of a lot of the industrial components on this, and yes, a rich societies, which the U.S. is a rich society, can make a number of choices. And we would become, somewhat less rich, but we're still a rich society. So we're not probably necessary. It's just really useful on there. But for other parts of the world, I think it is necessary. And for me, necessary is there are so many people who are going to live such horrible lives that we can make better. I mean, we can make the U.S. better, but there are some great advantages to living in a wealthy society on there that, we could. Without nuclear, okay, we're either going to have a much higher carbon footprint or a much less energy-intensive lives. And energy is such an enabler. And here, being able to travel, to be able to have the lights and have the heating and the air conditioning and I live in the South here. I have a hard time imagining not being able to have air conditioning when I want it. I've lived in the North. Not having central heating when I want it is both of those places are uninhabitable without central heating or air conditioning. I mean, I can't imagine, much of the coastal parts of this country, Houston or New Orleans without air conditioning. They would revert to swamps. I'm hoping that the next generation of people continue to build upon the good ideas of the prior generations, and it's probably one of the young generation who's going to have their hand on the switch when the first electrons hit the grid from the advanced reactors, because it's still we're still not on the grid yet, and it's still a few years. So the folks who are probably in the schools learning their science and learning their engineering disciplines are going to be the ones that set the course for the future. And so I hope that you guys can participate. Yeah, I say that I want to have a successful career, but my goals, my threshold on this at the end of the day is I want to see an advanced reactor put power on the grid. It has not happened yet. here, and I think that most of the folks who are in the nuclear enterprise, in the advanced nuclear enterprise, have that similar goal, and you're worried about, are our careers a failure? Because because eventually the only metric is, did we actually produce power? Because that's what the purpose for this is. And I've worked and helped the NRC and helped to see what we can't do to maintain the current fleet and help to make it safe, or keep it safe more than make it safe. But it is not, to me, that is unsatisfying on this. I think our next generation really needs to push for, how do we improve upon where we are now?
Well, that's a worthy goal, important goal. So, thank you very much. This has really been terrific. You said a lot.
You're more than welcome. Hopefully you found found most of this is useful.
Oh, very, absolutely. I don't think we don't have anybody talking about this, and we're trying to. And reactors were one of the big outcomes of the Manhattan Project. This clearly connects the dots with what started back in the 40s. And
So the technologies are similar. The goals are very different on there. We essentially, yes. Yeah, you can use the energy out of fission for very creative and useful things, whether it's nuclear medicine or power production, or you can use them as very destructive things that, our nation maintains a stockpile of nuclear weapons, and we still live in a world that has adversaries and unpleasant things, and and so both aspects of the power of the atom continue to be important today.